Concrete is used in nearly every structure where people live, work, learn, and play. It is part of the infrastructure that connects us. It's the material that helped build modern society and is a critical part of improving modern society for the foreseeable future. In fact, concrete is the most widely used building material on the planet. Let's start with the top 10 list. Then I'll go through each one in detail. 1. Communicate carbon reduction goals. 2. Ensure good quality control and assurance. 3. Optimize concrete volume. 4. Use alternative cements. 5. Use supplementary cementitious materials. 6. Use admixtures. 7. Don't limit ingredients. 8. Set targets for carbon footprint. 9. Sequester carbon dioxide in concrete. And finally, encourage innovation. To make sure that reducing embodied carbon remains a top priority throughout the project, it must be included in drawings and specifications that are communicated to the owner, contractor, and concrete suppliers. When it comes to embodied carbon, product manufacturing is paramount at every step along the way. I have 3 basic recommendations. Collaborate. The only way you can set your carbon footprint goal is to understand the capabilities of contractors and producers who will work on the project. Invite them in for meetings with your design team. Understand what technologies and concrete ingredients are available locally. Just because a product, like slag cement for example, isn't generally used in a market, it doesn't mean you should not specify or prohibit its use. Generally, the reason a product is not used is because there is no demand for it. You need to create that demand by permitting and encouraging its use. State your goal at the beginning of the concrete specification. In section 03300 of the specification, part 1, and make it clear what level of carbon reduction you are trying to accomplish for the project and for the concrete itself. It is also important to communicate carbon reduction goals in other ways. Most projects have pre-bid meetings, which can be opportunities to communicate carbon reduction goals for all products to all potential bidders. The next strategy is to ensure good quality control and assurance. Let me explain. Concrete producers design concrete mixtures to meet the needs of the contractor in terms of workability, for example, flowability, pumpability, finishability, and so forth, based on their local aggregates and then using sufficient quantity of cementitious materials to achieve the required compressive strength, which is higher than the specified compressive strength. This overdesign, that is, the difference between the actual average compressive strength and the specified compressive strength, is based on well-established statistical methods described in the codes and standards for concrete. If a concrete producer has a good quality control process and a history of consistent test results for a mix design, the overdesign can be relatively small, say 400 to 600 psi for 4,000 psi concrete. But if quality control or quality assurance testing is poor, then the overdesign can be much higher, 1,200 psi or higher for 4,000 psi concrete. There are well-established procedures for taking concrete samples, preparing test specimens, storing them on site, transporting them to a laboratory, and finally testing them in a compression testing machine or other apparatus. Concrete rarely tests well when testing protocols aren't followed. If test results constantly show lower strength, then the only way to overcome that is to increase overdesign, which generally raises cementitious material content. Lower overdesign means lower cementitious materials content. For example, going from 1200 psi to 600 psi over design would likely require 60 pounds less cementitious material, potentially an 8% decrease in embodied CO2. One way to provide some assurance that a concrete producer has good quality control is to require certifications for their manufacturing facilities, mixer trucks, concrete technicians, and plant operators. The same can be said of installers and independent testing laboratories and their personnel. And the same principles apply to testing labs. Make sure they are qualified and their personnel are certified. Next, let's talk about optimizing concrete volume. This strategy is just about employing good design practices. If a structural element, such as a column or a beam, is designed larger than required, then excessive concrete is being used, which increases embodied carbon. Alternatively, for a high-rise building, reducing the size of the columns might be critical to keeping the rentable space to a maximum. That means using high-strength concrete, which generally means higher carbon footprint. I suggest using life cycle analysis software to quickly calculate the embodied carbon of concrete elements, structural or architectural. Consider exposing concrete wherever possible. Finished materials have a considerable carbon footprint, and since exposed concrete can be attractive and is fire resistant without the need for additional protection, this is an excellent strategy for reducing the carbon footprint of the building. The other benefit of leaving concrete exposed is that concrete absorbs carbon over time through a process called carbonation. More about that later. There are several alternatives to Portland cement, but the most common are called blended cements. These combine ordinary Portland cement with other materials. The most common type of blended cement is Portland limestone cement, often called PLC for short, or technically ASTM C595 Type 1L cement. This blended cement combines up to 15% limestone interground with Portland cement to make a cement with a carbon footprint that is up to 10% lower than ordinary Portland cement, with performance that is identical to, and in some cases better than, ordinary Portland cement. The next strategy is obvious. Use supplementary cementitious materials. Nearly all concrete used today has some amount of supplementary cementitious materials, or SCM for short. The most common are fly ash, slag cement, and silica fume, in that order. However, there are others such as meadowkaolin, volcanic ash, rice husk ash, and ground glass, just to name a few. Some are waste byproducts of other industrial processes, and others are naturally occurring materials that require little processing and therefore have small carbon footprints. All enhance the performance of concrete when combined with Portland cement, including increased strength, increased durability, and enhanced workability. There is a complex chemical process that occurs between the SCMs and the Portland cement hydration byproducts, which contributes to these enhanced properties. The solution for this one is also easy. Just list all the types of cements and SCMs permitted by codes and standards. There is no need to limit quantities in this part of the specification. The next strategy is to use admixtures. Nearly every concrete made today uses some sort of admixture. Most affect the plastic properties in order to make concrete more workable, economical, shorten or lengthen set time, and so on. Without admixtures, concrete could not be pumped hundreds of feet in the air or transported hundreds of miles, and many architectural finishes could not be achieved. There are water-reducing admixtures that in effect reduce cement demand, accelerators that improve strength gain, and viscosity modifiers that permit concrete to flow into very tight spaces. As an example of how effective admixtures can be, using a water-reducing admixture that reduces water content in a mixture by 12% will result in a reduction of cement content by 70 pounds for equivalent slump and strength, and in a carbon reduction of roughly 10% for 4,000 psi concrete. Here is another simple solution. All admixtures that meet an ASTM standard should be permitted and listed in your concrete specification, and those that do not meet a standard should still be considered with proper submittals and technical backup. The next strategy is to not limit ingredients. All too often, there are seemingly random limits on material ingredients in project specifications that limit the concrete producer's ability to meet performance criteria, let alone reduce carbon footprint. Having unnecessary limits on the water to cementitious materials ratio is one example. In most cases, requiring a water to cementitious materials ratio is unnecessary and drives up cement content. There are times when a maximum water to cementitious materials ratio makes sense, mostly for cases of concrete exposed to freezing and thawing, but it is not necessary to call it out in the specification. The same is true for air content. It's only required for concrete exposed to freezing and thawing. Air entraining decreases concrete strength. For instance, a 10% decrease in cementitious material content for 4,000 psi air-entrained concrete compared to non-air entrained concrete for the same strength would roughly translate to a 9% increase in carbon footprint. Do not list a maximum or minimum cement content, maximum or minimum SCM content, or quantity of admixtures. Do not limit water used for making concrete to potable water. There is an ASTM specification for water used to make concrete. My recommendation is to provide a table in your specification for concrete listing the important performance attributes for concrete. Each project will have different values depending on the project requirements. For this example, Class 7 concrete, exterior pavements, would have a water to cementitious materials ratio and air content limit because of its exposure to freezing and thawing, which is spelled out in ACI 318 and ACI 301. And finally, concrete that will not be stressed for significant time periods can be tested at later ages, which means higher volumes of SCMs can be used, resulting in a lower carbon footprint. The next strategy is one of the most important and one of the hardest. You have to set targets for carbon footprint. This strategy is for those who have some knowledge of life cycle assessment, experience with environmental product declarations, and an understanding of global warming potential for the targets to be implemented effectively. First, resist the temptation to set carbon footprint limits for individual classes of concrete. In effect, this is the same as providing prescriptive limits on materials and leaves little room for the contractor and producers to innovate and meet the project performance requirements, including budget and schedule. The best approach is to use a whole building life cycle assessment to set a carbon budget for all the concrete on the building. It is still necessary to have a general idea of what the carbon footprint of each mix design will be to set a carbon budget for the building. Many concrete companies have published EPDs for concrete, and most would be willing to publish EPDs specifically for a project. NRMCA has published a cradle-to-gate life cycle assessment of ready-mixed concrete and industry-wide EPD for concrete. Armed with this information, you can conduct an LCA to determine the embodied impacts of concrete of a benchmark building using typical concrete mixes with typical amounts of SCMs, and a proposed building using concrete mixes with high volumes of SCMs. Keep in mind that concrete requiring high early strength should be limited to around 30% replacement of fly ash or slag. Concrete that does not require early age strength, such as footings, basement walls, and even some vertical elements such as columns and shear walls, could have as much as 70% fly ash and/or slag and could be tested at 56 or 90 days instead of 28 days to account for slower strength gain. high-volume SCM mixes can be identified from the industry-wide EPD or from published product-specific EPDs from different regions. Once you've calculated the carbon footprint for the proposed building, list that target in your specification as shown here. The next strategy is to sequester carbon dioxide. CO2 can be captured or sequestered in concrete through natural processes or carbon capture technologies. Carbonation is a naturally occurring process by which CO2 penetrates the surface of hardened concrete and chemically reacts with cement hydration products to form carbonates. For in-service concrete, carbonation is a slow process with many dependent variables. The rate of carbon uptake decreases over time. This is because carbonation decreases permeability and carbonation occurs from the surface inward, creating a tighter matrix at the surface that makes it more difficult for CO2 to diffuse further into concrete. While slow, the carbonation process does result in an uptake of some of the CO2 emitted from cement manufacturing, a chemical process called calcination. Theoretically, given enough time and ideal conditions, all the CO2 emitted from calcination could be sequestered via carbonation. Consider permitting the use of recycled aggregates made of demolished concrete on the project and possibly require that those recycled aggregates be exposed to air for 1 year before being used. In some cases, a certain percentage of recycled aggregate can be used in concrete, or it can be required that all aggregate base or fill be made of crushed concrete. The use of carbon mineralization processes such as injecting CO2 into concrete or curing in a CO2 environment should be encouraged, as well as the use of artificial limestone aggregates. It is also worth considering the use of exposed concrete on the project, both on the interior and exterior. This has the added benefit of reducing the amount of finished material in addition to absorbing CO2 throughout the lifetime of the building. The final strategy is to encourage innovation. Of the 10 strategies, this is probably the most challenging. Throughout this presentation, I've talked about the importance of not listing specific products or naming certain technologies. Instead, simply list the standards that one must meet. The problem with this approach is that it permits innovation but does not necessarily encourage it. If a standard has been met, likely the product is considerably past the innovation stage. The product or process was likely invented, worked within a standard, modified the standard, or modified to meet the standard. For an innovative product or process to be successful, demand must be created within an existing process that's often rigid. However, there are some things that can be done to help create demand for innovative products. My recommendation here goes back to strategy 1, communicating the carbon reduction goals to contractors and producers during the design process is critical. Let them know that you are looking for innovative solutions. Design charrettes would be a great place to engage engineers, contractors, and concrete producers. Ask them to bring opportunities to the table. Most sophisticated producers are experimenting on new formulations all the time. Ask them to discuss some of their low-carbon concretes. There is no silver bullet to making concrete with zero carbon footprint. It can be done, but not at the volume and cost demanded by today's building owners. For some concretes on a project, the carbon reduction might be 90%, others closer to 70%, and still others around 30%. All these reductions lead to concrete with a significantly lower footprint than similar projects. If you choose to set carbon footprint targets, this will lead to the greatest reduction. But always refer to this top 10 list when implementing ways to reduce concrete's carbon footprint.